Our next speaker is Scott Clark. He is the CEO and co-founder of SigOpt. He is passionate about empowering experts to achieve their full potential with optimization solutions. He conceived the idea for SigOpt while completing his applied mathematics PhD at Cornell and proceeded to build and open source the metric optimization engine at Yelp to help solve this problem. The process taught him that optimization needed to be productized to be effective for enterprises, which led him to found SigOpt in 2014, which has subsequently been funded by Y Combinator, Andreessen Horowitz, Bloomberg Capital, DCVC, In-Q-Tel, and others. SigOpt now helps firms and academics around the world accelerate and amplify their research through optimizations in fields from machine learning to algorithmic training and beyond. Scott holds a PhD in applied mathematics and an MS in computer science from Cornell University and BS degrees in mathematics, physics, and computational physics from Oregon State University. Please join me in welcoming Scott to the stage.
Hey, everybody. Thanks so much for joining me today. I'm going to be walking through some lessons learned from working with algorithmic traders and large technology companies from around the world. I'm going to do a brief overview of what we do just to contextualize things, and then dive into 3 takeaway lessons that you can hopefully use and apply when you go back to work on Monday. If, for whatever reason, I gloss over something you want to dive deeper on, we have our full team in the back at the booth, and we're happy to dive deeper or whiteboard or do whatever you want to dive deeper into any of this. So please come visit us after the talk. First up, and this was an introduction, so I'll go quickly here. I founded SigOpt really with the idea of wanting to accelerate and amplify the impact of modelers. And what this really means is we firmly believe that there's some domain expertise and context awareness that you bring to bear on a problem that differentiates you from your competitors. You know something that no one else does, and our goal is to make sure that you get to that result, that impact of that knowledge, as quickly and efficiently as possible. And our goal is to really differentiate whatever edge you bring to the problem. So as you heard in the introduction, I've been doing this for a long time, 10+ years of doing everything from tuning HPC algorithms at Los Alamos to tuning advertising systems at Yelp. And basically one thing I found that no matter wherever I went, there were tunable parameters. Experts would spend years, sometimes decades, building big, complex systems, only to, at the end of the day, have to tune and tweak them to get to the best possible results. In academia, getting to better results meant better papers. At Yelp, getting a better advertising system meant more money. And at the end of the day, it meant whoever was the lowest person on the totem pole had to go in and tune all these knobs and levers. We jokingly call this grad student descent. Obviously, there's a lot of techniques out there to do this, some better than others, and I'll go through that in a little bit here. But ultimately, the goal of SigOpt is to take this off of the plate of the researcher. You know something special, and you want to apply that to the world, but doing high-dimensional optimization in your head is not that special thing that you know. So SigOpt was founded to solve that problem. We've been doing it for about 5 years now, and are continuing to grow with clients around the world. And one reason why this is super important is not all modeling is created equal. Not all AI is the same. There are some models where simple techniques work incredibly well. There are a lot of models like this. Linear regression, logistic regression, some of these tried and true techniques really work efficiently for very certain problems. And there are a lot of those problems out there. And if you're not doing any AI today, you can get a massive gain by just attacking these with one-size-fits-all tools, automatic tools, and things like that. But as you go up the value chain, things get more and more complex. Again, that domain expertise and context awareness that you bring to bear on the problem really starts to matter. Gartner calls these differentiated models. Models where, again, you're hiring experts. You're hiring machine learning engineers. You're hiring data scientists. It's not about empowering a business analyst. It's about taking the bleeding edge and pushing it a little bit further. And often what we see is there's not only a power law of the number of these models, but there's also a power law in the value that they produce for a firm. The trading strategy, that ultimate model that's actually hitting the market, may have 10,000 times more impact on your P&L than the model that decides whether or not you should delay your payment to a vendor or something like that. And at the end of the day, these are the ones that drive the business forward and the focus area of the advanced tools like SigOpt. And what we see is that we're not the only people that believe this. So this was a study done by Accenture where they interviewed 8,300 global enterprises. 80% of them had deployed AI in some way across all three of those different areas of differentiated or custom or kind of more of a business analytics 2.0 type approach. But there was a massive opportunity cost for using the wrong tool for the job. 41% of the impact was taken away when you just use that one-size-fits-all solution, when you didn't apply that domain expertise and context awareness. Again, you know more about your business than anyone else in the world, and you want to amplify that. They expected a 33% gain by switching over to these more custom bespoke solutions. And I know a lot of you in this room are probably working on those solutions or have people working on those solutions within your firms. So there's massive opportunity cost, and doing AI doesn't mean it's solved. So the way that SigOpt works with firms like this is by not replacing their ML system, not necessarily just coming in and saying, we're going to take everything from end to end. We want to bolt on top of what you've built in-house. So again, there are tunable parameters for every single model you're building, from the simplest random forest where you need to select the number of trees to the most complex neural network where there's learning rates, batch sizes, dropout rates. The more complex something gets, the more tunable parameters there are. And ultimately, there's a lot of performance locked up in those parameters. Sometimes the difference between a winning strategy and a losing strategy. An untuned random forest might beat an untuned, more sophisticated method. But by tuning it, you might be able to see what the real winner is. So SigOpt bolts on top of these systems. You say, this is what I can tune. All the integers, categories, floating point, magic numbers that would otherwise just creep their way into your config files. We then suggest different things to evaluate. You evaluate that within your system, so all of the IP, all of the data, everything like that lives with you. Only an objective function, a response, comes back to us. This was the Sharpe ratio. This was the accuracy. Whatever it is that means business value to you. We learn from that to suggest the next thing and repeat. And what this does is guides you into the best configuration, the best versions of your models, quicker, faster, and better than alternative techniques. And we've been doing this with a lot of firms around the world over the last 5 years. We help asset managers with over $300 billion of combined assets under management tune their most sophisticated models. We also help technology firms, streaming services, and the US intelligence community tune their most valuable differentiated models. And we've learned a lot by doing this over the last 5 years about what it takes to build a good modeling stack, what it takes to decide which tools are worth standardizing on, where you want flexibility, et cetera. And that will be the second half of this talk. But it goes without saying that getting better results faster and cheaper can make a big impact. This is a quote from Matt Adareth, a managing director at 2 Sigma, one of our large users. And at the end of the day, this can really empower teams to get the most done. This can empower them to leverage that domain expertise and, again, really differentiate themselves against their competitors. So I'm going to break this into 3 lessons, 3 easy takeaways. I know it's a long conference, and so if you can just take away 3 things from this talk, I'll be very happy. If you want to dive deeper and hear the next 30 things to lessons learned, come see us at the booth. So first up, I'm going to talk about balancing flexibility and standardization. I'm going to talk about maximizing resource utilization and unlocking net new capabilities. So when it comes to balancing flexibility with standardization, I'm going to talk about the entire modeling stack or platform. Oftentimes, this is a big, complicated endeavor to understand. I have a very high-level view of it here, but you can break it down into large chunks of there's data management issues, there's the modeling itself, there's this experimentation and optimization. Ultimately, you need to do a simulation, a back test, or an evaluation on these models to see if they work. Eventually, you put them into production. That can mean very different things for an IoT firm, a high-frequency trading firm, or if you just have a large streaming service. And then underlying all of this is the compute environment. So this can look really daunting if you don't have a stack in place today. And it can be very powerful to just use an off-the-shelf solution if you're doing nothing. But as you start to graduate from those methods and look for more sophisticated tools, I'm going to talk about ways that you can trade off leveraging flexibility or customizing things yourself. So our recommendations, having worked with these firms around the world, is to customize and differentiate yourself with your data and your model execution. So again, you probably have some unique data. You probably have something that's a secret, whether you're an insurance company and you know all about the premiums of your users, or you're an investment bank and you have the information about your clients. There's something unique about that, and this is the way that you perceive the world, and there's ways that you can do that differently than, is there a cat in this picture? At the end of the day, model execution, again, is very customized to your use case. The SLA you need and the uptime and the response you need, if you're a market maker, is very different if you're doing longer-term bets and doing more statistical arbitrage. So again, customizing there can allow you to use the right tool for the job. Flexibility is also incredibly important. Obviously, it's very difficult to hire the most sophisticated machine learning engineers and data scientists out there, and they like using the best tools. And those best tools are constantly changing. The same person who loved scikit-learn 10 years ago might love TensorFlow or PyTorch today. And 10 years from now, or even 2 years from now, there's going to be some cool new tool, reinforcement learning, or whatever it may be, that they want to leverage. And so allowing them to maintain flexibility and use that right tool for the job is really important. So standardize on the edges based off of your custom needs, but then allow flexibility on the modeling, but also customize the way that you evaluate your models. This is probably one of the most important lessons and the biggest pitfall we see when we talk to customers around the world. A model and an optimization engine is only as good as the target you point it at. In academia, you can publish papers by just saying, I got a better accuracy on this, or my log loss was slightly lower than someone else. Accuracy and log loss is not the same as profit. You need to be able to equate what your models do with how you make your money. That might mean a really sophisticated, robust backtesting system for an algorithmic trading shop. It might mean saying, how does this actually affect the bottom line for a fraud detection algorithm at a credit card firm? At the end of the day, again, your team and your models will only do what you tell them to do. So making sure that this is as customized as possible to what you constitute success is very important. And then at the end of the day, the compute environment is, again, something that can be a little bit interchangeable, and there's amazing tools out there. So there's lots of ways to do this, and I'm going to say that focusing on optimization and experimentation in the middle of the stack allows you to standardize without constraining. So by picking a tool that allows you to use any hardware platform, any modeling stack, and any evaluation function, allows you to say, I know what I want, I know what tool I want to use, I just want to use it the best I possibly can. The second big lesson is how to maximize resource utilization. So everybody wants things to be better, faster, and cheaper. Resource utilization is about doing things faster and cheaper. And this is a really difficult problem, and I'll show you here an example. Imagine I just dropped you in the cockpit of this F-15, and I said, tune all of these different knobs and levers, and a couple hours later, I'll tell you how well you did. And then repeat that process, and if you do it really well, you might make a lot of money. If you do it really wrong, the plane might crash. Your data scientists and machine learning engineers are faced with this literally every day. It's called a bunch of different things. HyperParameter optimization is the most common, but it can be model tuning, playing around with the model, experimenting, all these sorts of things. And there's lots of ways that people attack it today. But again, every model has these, whether you're tuning them or you're ignoring them. Default parameters is still a choice. And there's been a long history of tuning these models, all the way back to the 50s when a lot of these original computational techniques were developed. You can do things like manual search. This is really nice because it allows you to apply any intuition you have about the system. It allows you to kind of feel like you're involved in the process. Unfortunately, it ends up being incredibly non-scalable and inconsistent. Humans are good at many things. Humans can still beat computers at lots of things, even if computers can beat them at chess or Go. But doing 10-dimensional optimization in your head is not something the human mind was built to do. So just like chess and Go, high-dimensional optimization is something that the computers have an edge at. So if you're not going to do this by hand, well, might as well just try everything. This is grid search. This is the brute force approach. I know I've got this problem. Let me just try every configuration in that cockpit and then see whichever one was the best. Unfortunately, while this can work for very simple problems, if you're tuning 1 or 2 knobs, it suffers from the curse of dimensionality. It grows exponentially with the number of things you're tuning. So as your experts use more sophisticated techniques, this quickly becomes intractable. Waiting a few hours might be acceptable. Waiting until the heat death of the universe is impossible. So what's become really popular in the academic literature, and there were some papers about this several years ago, was just try random stuff. It tends to work a little bit better than these other techniques. This is akin to trying to climb a mountain by just jumping in an airplane, closing your eyes, jumping out, and hoping you land at the peak. And then just doing that over and over again. So it's very scalable, very parallelizable, but again, inefficient and inconsistent. The big difference here for all of these methods, grid search and random search, is that they don't learn from previous mistakes. They will continue to do the same thing regardless of what you've actually observed. And this is even true for more advanced variants of random search, like hyperband, or things that can speed up that randomness, but ultimately still rely on just try something and hope it works. So in the 80s and 90s, there was this big push of different global optimization strategies based off of physical phenomena. Evolutionary search tried to mirror the biology and how evolution works. Things like simulated annealing and particle swarm drew from physics. These can be extremely powerful and quite a bit better than these other techniques. They tend to allow you to use more sophisticated, optimize over more sophisticated response surfaces, et cetera. But at the end of the day, they're still incredibly inefficient, insofar as they require a large number of samples to simulate that real-world phenomena and then converge into local optima. When you're annealing steel, you don't just instantly get to the best lattice structure. When things are evolving, they don't just instantly become a super predator. At the end of the day, it takes a lot of effort, a lot of population to slowly evolve into things. Which is where Bayesian optimization comes in. This became really popular kind of in the turn of the century. Some of the seminal papers were written in the early 2000s. It's become quite a bit more popular over the last 10 years. There's been workshops at ICML, NeurIPS, AI Stats, CVPR, things like that. The concept of Bayesian optimization is how do we leverage what we've learned so far to as efficiently as possible sample this expensive space? And this can be incredibly efficient when configured well. And that's the big gotcha. So I'm guilty of writing one of the most popular open source libraries in this field. And at the end of the day, the biggest feedback I got from it, even after it got 1,000 GitHub stars and I gave talks at like 50 different companies, was, great, you took my optimization problem and you turned it into an optimizing an optimizer problem. I still have a problem. And that's because these techniques, while extremely powerful, are quite a bit more complex than the others and require a lot of knowledge and trade-offs and things like that. And that's ultimately what Sigopt is designed to do, to alleviate this problem, to put it all behind a simple API, to be able to do things like high parallel asynchronous sampling, to be able to handle multiple metrics, constraints, and all of these issues that you might have underneath the hood. What we've done is we've taken an ensemble of all of these techniques where we automatically trade off and tune the optimizer. So you just say, this is what I can tune, just get me those best results. And this means real-world difference. So in this use case by 2 Sigma, they had a task where they were using an open source optimizer, very popular one from the field, another one of those 1,000-star GitHub repos. And when they applied Sigopt to the problem, the tuning went from 24 days to 3 days. And they got a better result on their objective metric. So this is against cutting-edge open source. This isn't against grid search or random search or something like that. There's a lot to be locked up in optimizing the optimizer itself. And this can be monumental for teams. This means being more iterative. This means getting better results. And this means less opportunity cost in a highly competitive environment. The final lesson I'll leave you with is unlocking new modeling capabilities. So it's not just about doing what you're already doing today, but faster and cheaper. It's about really saying, how do we change what we're doing today? How are we constrained by the fact that we have these suboptimal optimizers? What does this change about the way that I even approach problems now that I know I can hit targets really well? Well, it allows you to do a handful of things. Tune things that were otherwise intunable. So if it takes days to evaluate a method, you might say, listen, I can't optimize because it just takes too long to go. There's no way that I'm going to wait a year to get a result or something like that. Well, by using more sophisticated techniques or using some of our advanced features like breaking that task up into subtasks and learning from them, you can start to attack these problems more directly. Another thing that you can do is say, I want to optimize multiple things simultaneously. So instead of just saying, oh, what's the best possible Sharpe ratio I can get? Well, a good Sharpe ratio is great, but if you're only trading on a book of $10, it doesn't really matter. So maybe trading those off and being able to say, as an expert, what's this efficient Pareto frontier? What's this best possible trade-off between these metrics that I want to select? That can be extremely powerful, and basically it points to, now that you have a way to hit targets, it allows you to build better targets, as well as exploring some of the things that you would otherwise say, again, are intractable, or you might only look at modularly. Maybe you say, well, I'm going to tune all the feature embeddings first, then all the architectures, then all the hyperparameters. By looking at these things simultaneously, there can be massive gains that would be otherwise lost. So again, the lessons here are trading off scalability and flexibility, and really making sure you maximize the resources that you have. And then think about how you can unlock net new problems with the goal, again, of really driving that wedge deeper and deeper and saying, I'm going to differentiate myself from the competitors because I know something secret. And I just want to make sure that I'm as equipped as possible to run as fast as possible in that direction that only I know. So I'll leave you with that. If you'd like to try our solution, please come talk to the great people at the booth. There's a great ebook that just got released yesterday from This Week in Machine Learning that we co-sponsored. I highly recommend downloading it. It talks about all of the different machine learning stacks at like Facebook and LinkedIn, and some of these trade-offs in quite a bit more depth. I'm going to be going over a webinar in a few weeks on some of these more advanced techniques in a little bit more depth, kind of drawing from our 20-plus published papers at like ICML and NeurIPS and things like that. And then if you want a conference that's just dedicated to machine learning platforms, I recommend you check out TWIMLCon, which is coming up in October. Excellent. Thank you all.
Thank you so much, Scott. Thank you.